On the front of the note packet, these two Bower questions are here just because you're going to need to know them this chapter. And so when you ask me about it in a couple days, when you're like, what does STP mean? What is that? What am I supposed to do with that? I'm going to say, look in front of your notes because it's there. Okay? So we need to know the conditions for standard temperature and pressure and the conversion between Celsius and Kelvin. So we actually need numbers and units for temperature and pressure in STP, standard temperature and pressure. Who wants to take a guess at pressures? Kind of has to do with what we did in chapter 13. With those numbers. No, that's wrong. Like, didn't we have like ATM and KPA? 101.3 is one of them. And that was KPA. That's a PA. 760, what was the unit on that one? mmHg, millimeters mercury. We're not going to use that with STP this time. But then the atmospheres, ATM was the other one. What was the number with the ATM? A 1 ATM. Yeah. So if I ever say standard pressure, you're going to pick one of those two. Okay? What about temperature? What is a very common standard temperature? In Celsius, because we don't use Fahrenheit. What? Celsius? That's Fahrenheit. 100 degrees Celsius is when water boils, right? That doesn't happen normally, so we're not going to say that's standard, but it's a good guess. What would be 50 is like liquidy. 0 degrees Celsius is going to be our standard temperature. But we also need to know it in Kelvin. So, to get to Kelvin from degrees Celsius, do I add or do I subtract 273.15? Add it. This is from chapter 3, you guys. 11 chapters ago. Back in like September, we did this stuff. So, if it's 0 degrees Celsius for standard temperature, what would that be in Kelvin if you plugged in 0? 273.15. And then when you put K for Kelvin, you don't have to put a degree symbol. It's not needed. It's not degrees Kelvin, it's just Kelvin. No, but it's irritating. Okay, so if you ever see STP at STP, then that means that you're going to use these information. Anytime we use temperature this chapter, you're going to be given it either in Celsius or Kelvin. If it's in Celsius, you have to convert it to Kelvin. So there, we put the equation for us on the front. Okay? Here we go. This chapter is all about gases. Maybe. So we're going to talk about the properties of gases, some gas laws, what an ideal gas is, and how gases move. It's a lot of rhyming this chapter, by the way. So the first vocabulary word of our 4 vocabulary words that are on the vocab on its learning is compressibility, which is a measure of how much the volume of matter decreases under pressure. So gases are easily compressed. We learned in chapter 13 that gases have a lot of space in between them. They're moving around constantly, they may collide with one another, but there's a lot of space between. And since there's a lot of space between, we can reduce that space, making them closer together, and that's how you compress a gas. Okay? So this picture shows how if you have some particles and they're in a lot of volume, a lot of space for it to move, they can just move around, whatever. It's low pressure compared to when you compress it down, so you reduce the amount of volume that it can move around in, that makes a higher pressure. Pressure is measured by collisions of the particles. Okay? So we're going to talk about the different effects that things have on gas pressure. The first is the amount of gas in the substance. So collisions with the walls, with themselves, collisions in what make up gas pressure. Okay, that's how we measure gas pressure, is by the number of collisions. So by adding gas, you increase the number of gas particles, which would then increase the number of collisions, because there's a higher probability that they're going to run into something when they're moving around. Okay? Did everybody write down their blanks? Because I covered up. So in this first example on the left, we have like, ooh, look, there's a collision when you have an arrow and it's pointing in the direction. Just like that, Brian. And then when you throw in a whole bunch more, there's going to be a lot more pressure because they're going to run into each other a whole lot more. Okay? Make sense? Hopefully? The next one is volume. We kind of already saw this with compressibility. So the pressure exerted by a container in the gas can be raised by reducing the volume. So the more gas that is compressed, so the smaller the space in which it can move, the more pressure is exerted. And this is another picture like what we saw with compressibility, where when it has more space to move around, it's going to have less pressure than when it has less space to move around. We are almost done with notes, by the way. Okay, next is temperature. When you heat something up, it increases the kinetic energy. Kinetic energy is the energy of movement. Okay, we've all heard this before. So when you heat something up, the temperature raises and also the average kinetic energy raises. And so because they're moving a lot more, they're going to be making more collisions. So if they're making more collisions, the pressure is going to increase. Okay, so it has more energy, more collisions, more pressure. They're all kind of the same thing. This kind of stuff is going to be important because I'm going to say, which of the following factors increases the pressure? And then I'm going to have like A, reduce the volume, B, increase the volume, C, lower the temperature. And you're going to pick A, reduce the volume, because that increases pressure. Okay? So here is showing how actually when you increase the temperature, you also increase the volume, and then it increases the pressure. Okay, so our first law that we're talking about today, and our only law we're talking about today, is called Boyle's law. It's named after that handsome gentleman up in the corner. If temperature is constant, as the pressure of a gas increases, the volume decreases. So Boyle's law states that for a given mass of a gas at a constant temperature, meaning temperature is not included, the volume of the gas varies inversely with the pressure. We're talking about inversely proportional and directly proportional this chapter. You may have heard this in math class before. This terminology, okay? So, like, this is another way to think about it. If I would say, according to Boyle's law, if you would reduce the volume, so you're lowering the volume, how does that affect the pressure? Well, it's inversely proportional. Inverse means they're opposite. So it does opposite of what the other one does. So if volume is decreasing, what's the pressure going to do? It's going to go up. It's going to increase. Okay, so hopefully you know that inverse means opposite, and whatever I say, it do the opposite for the other choice. Okay. Well, we're super creative with our equation, and we use P's and V's. P stands for pressure, V stands for volume. Okay. We have P1 V1 equals P2 V2. All that means is the ones and the tunes, is the ones are what it originally started at, and the twos are the new conditions, okay? P, we're going to plug in pressure stuff. So pressures can have units of ATM, the KPa, or the mmHg from last chapter. All of those apply still, okay? So and it doesn't matter which one it is. The only thing that matters is that it's the same unit for both P's on either side, okay? Which I will not try to trick you and give you different ones. So if it's ATM on the left, make sure it's ATM for P2 as well. For volume, the unit is going to be the same as the unit that's on our mole map. Does anybody remember the unit for volume on the mole map? Liters. Yeah. So volume is going to be in liters. Normally, I just give it to you in liters. You may occasionally have to change it from milliliters, but not very often. So with these equations, these are like plug and chug, like chapter 3 was. So I'm going to give you 3 numbers out of the 4 variables to plug in, and you just solve the last one. So it's just, once you plug and chug, it's just algebra, making sure you're doing it the right way. Okay? So we have one example, and then that's it. Sound good? Fantastic. Okay. So a balloon containing 30 liters of helium gas at 103 kilopascals. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25 kPa? Assume that the temperature remains constant. First thing I want to say, this last sentence in parentheses, it's really unnecessary information. There's no temperature involved in this equation, so that's just kind of like trying to trick you, throw you off kind of thing. Okay, so the temperature is not important. We do need to figure out what our 1's are, what our 2's are, and what we're solving for. So I'm going to go ahead and list them in a way so that the 1's are together and the 2's are together, so I know what to plug in the right place. Okay? 1's, I usually, like whatever number comes up first, I usually call that a 1. And then 2's are whatever comes next. So, starting back to the problem, we have 30 liters of helium gas. It's liters, so is that a volume or a pressure? It is a volume. And since it came first, I'm going to label that as V1. Okay? So 30 liters of helium gas at 103 kPa. That's our next number. Is that a pressure or volume? A pressure. Is it 1 or 2? It is 1. If you have a trouble with this, my hint is, there's 2 ways to see. Okay? The word at is saying that these 2 things are related, meaning they should have the same little subscript number when you plug them in the variables. Okay? Another thing to think about, they're in the same sentence. And most of the time, when the 2 numbers are in the same sentence, they are going to be related, so they should both be 1's or they should both be 2's. Okay? So I'm going to put the 103 kPa for P1. Now, we have the 1's filled out, so now we're going to have to solve for a 2, but which 2 are we solving for? So it says, what is the volume of helium? Okay, there's our question. What is the volume? So my question mark, if I've already found V1, then I'm going to be solving for V2. So I'm going to put a question mark next to V2. Okay? When the balloon rises to an altitude where the pressure is only 25 kPa. I have 2 things here. It's in the same sentence as the volume that we're trying to solve for. And we only have 1 pressure to fill in left. So that's going to be where our 25 kPa goes to. Okay? Now it's time to solve. So, I'm not going to plug in the units, but I'm going to take 103 times 30. You can put this 0.0 or you don't have to, it's up to you. Equals 25 times, and then for V2 you got a couple options. I plug in V2 just because. You could plug in just a V. You can plug in an X or a different variable to solve for, but we're solving for it. Do you guys need me to show step by step how to solve for it, or do we know what to do? Show it? Okay, so can somebody take 103 times 30 and tell me what that is, please? 3,090, okay, equals, and then I still have 25.0 times V2. So now, which one am I dividing by? 25. The 25, because I have to get V2 by itself. So I divide both sides by the 25.0, and then V2 is equal to whatever that is divided. 123.6. All right, 2 people said it. Our unit is going to be liters, because it's volume. And then we had to know how to round to sig figs, so you look back at the original problem and the numbers in the original problem. We need to round to 3 sig figs. So we're going to have 123, or I'm going to round it to 124 liters. Okay? And that's it.